All right. Okay, we'll go ahead and get started. Um, how's everybody doing? Good. All right. That's good. It's week 7. It's uh, it's it's week 7. I don't know what else to say. All right. Okay. So you guys have the midterm on Wednesday, and I tried to describe that on Friday, what to expect. Um, yeah, just finishing writing it up right now, and yeah, I'm no surprises. What I've talked about on Friday is what you can expect. Okay. Um, all right. Well, we'll continue in our talk about classification methods, and and today's topic is just a very brief intro to support vector machines, which sounds so cool, but I mean, like the name is so cool sounding, but I mean the technique is pretty simple. Okay, it's very simple, and I spent sorry, I'm gonna have to do a whole bunch of handwritten notes today because I spent a bunch of time like making pretty pictures, but then like typesetting all the stuff I didn't do. So anyway, so the idea with support vector machines is that you've got some. We're going to start off with this. We've got some data, and here I've got two-dimensional data, and I've labeled them. So I guess these would normally just be dots, but I labeled them with pluses and minuses because that's how a support vector machine system is set up. You've got points of one class are labeled positive, points of the other class are labeled negative, and that's what we do. And this is in 2D, but you could also imagine this existing in higher dimensions. And the idea is, can you draw, in 2 dimensions, you would draw a single linear boundary, a straight line, to separate the two classes. And in higher dimensions, you would draw some kind of plane, a hyperplane in higher dimensions, okay? And we have to start off with the completely separable case, okay? And so if you look at this, how would you draw the boundary between your positive and your negative values, okay? And there's a lot of kind of possible lines we can draw. So like we could draw, we can draw one like that. We could draw another one, and these are all these would all have like 100% classification performance. Okay, they would all get it correct. We could draw something in between, and probably the one in between, intuitively seems like that might be the best or something, but that's just kind of the idea. We want to draw some kind of boundary between the two sides, okay? And so, so I'm going to just show you a bunch of kind of possible boundaries, and so here I've drawn this near vertical line, or just this very steep line, and what I've labeled or I've circled kind of the points that are closest to the boundary, okay? And so, so this point up here is closest to the boundary, and this point over here is closest to the boundary. And so I've circled these points, and I've kind of created dotted line margins, okay? Dotted lines that are parallel to the things. I don't know. So
that depends on the boundary.
It depends on the boundary that you draw, exactly. So this the middle line is the boundary, okay, and then this is kind of the closest positive point to boundary, and this is the closest negative point Okay, and then these are these are both kind of parallel to the boundary. Okay, so these are kind of just some ideas here. I guess I'll save this for something.
They don't have to be equidistant.
So here, the way we've kind of done it is whatever distance these two are, the boundary is in the middle between the two. Okay. All right, and then so here's like one, and then I'm just kind of like rotating, and you can see like if I just rotate the angle a little bit, the kind of the distance to the boundary increases. Okay, so we can see kind of increases like this, and then if I get to here, now we have actually 2 points that are equally close to the boundary. Okay, and then if I kind of just rotate it further, then the points that kind of define the boundary change. Okay, and so here's one here, and then as I kind of continue kind of rotating the boundary, we can see that this no longer defines the boundary, and then as it comes here, this point will become the line, or the point that becomes closest to the boundary, and then as we continue kind of rotating it, the margin of the boundary gets more and more narrow. Okay, so these are all kind of, but yeah, as we change the boundary, the points that are closest to the boundary and kind of activate them change. Okay, so this is what took me so long, and I was like, oh gosh, okay. But anyway, so this is what we have, and so which boundary are we going to pick? Well, the support vector machine says the boundary that ends up with the widest margin, that's going to be the one that we pick. Okay, and so that's going to be this one. Okay, so visually we can kind of see this, right? But how would we go about calculating it? And it's a non-trivial answer, and I don't even have a good answer for how to go about it. But this is what support vector, the support vector machine's kind of method, classification method, would do. Is it would pick this because it has the widest margin. Okay, so it says so SVM says the best line to pick is the one that maximizes the margin. The margin is defined as kind of the perpendicular distance from the decision boundary to the closest points on either side. And as we saw, the closest points to the decision boundary depend on the decision boundary that's chosen. Okay, and these points, in our case here, these 3 points, because these are the kind of the 3 that are closest to the decision boundary, and these are actually the ones that just define the decision boundary. Okay, once you have these 3 points, the other points actually don't even matter, and so these ones are known as the support vectors. Okay, because the points, we're thinking the points as in higher dimensionality, more than 2 dimensions, we can think of these as vectors in space. Okay, and these are known as the support vectors. Okay, and so so here is kind of the margin, and we want to pick the boundary where this margin is maximized. Okay, and so these are non-optimal margins or non-optimal boundaries, and we can see their their margin is a lot smaller. Okay, and so I'm going to just go back to this picture. Okay, so this line here, this vector, this one is going to be, we will call this our margin. Okay, so this is, we want to maximize this, and so what we're going to do is we're going to we define this boundary as y equal to, I'll pick a better color here. So we're going to have y is equal to W transpose x plus b. And for the boundary, we're going to define this as 0. So if there's some new point x, okay, right on the boundary, these new points would get classified as 0, neither positive nor negative, okay? So if I'll call this x new, if x new is on the boundary, kind of the boundary rule, the result of this, result is 0, okay? So not classified either positive or negative. Okay, and if we have something that is on the boundary, okay, so this point, so if this is y is equal to W transpose, and we have some new point, either this one or some other point right on the boundary, okay? When you plug it into kind of this W transpose plus B is kind of our decision rule. We're gonna define this as equal to +1, okay? And then anything along this boundary, okay? We're gonna define this as -1. So this is how we're going to go about to define this. And what we want to do is we want to figure out how to maximize this margin. Okay. And so let's see. Can I say this? Okay. No. So I'll call this sketch 2. Okay. Okay, so what we'll do is, if we just take 2 points that are on this, so I've got a point here, and I've got a point here, okay? This looks at, they don't necessarily have to be, but this vector, this black one right here, this is going to be the vector, if we call this x1, and this is x2, okay? It's just going to be x1 minus x2. Okay, so this is just some vector x1 minus x2, okay? And we want to dot this in this direction that's kind of perpendicular to the margin, okay? And what we have is earlier we have defined that we've kind of said, for this point x, if we call this one x1, so this is W transpose x1 plus b is equal to +1, and then we have W transpose x2 plus b is equal to -1, right? So this is what we said. This is the kind of the -1 boundary, and this is the +1 boundary. If we kind of try to solve these things from each other, and like if I subtract the 2 from each other, I'll get W transpose x1 minus W transpose x2, and then the b's cancel, and then I'll get +2, right? So I'll get 2, and so I get W transpose x1 minus x2 equal to 2. Okay, and to kind of figure what this is, we can say, you know, we want to know what that is. So I can't divide by W, but what I can do is I can multiply it by 1 over the norm of W, okay? And so we'll define this portion here, we'll call this the margin, because what this does is it takes x1 and x2 and it basically dots it, okay? It dots it. If we look at what W over W is, what this thing is, W transpose over the norm of W is that we are dotting this, like if you imagine some kind of, this to represent, you know, the direction, we're dotting this vector onto this direction here, okay? And so, so that is how we define this distance, okay? And this is going to be our margin, and we want to maximize our margin, okay? Okay, so we want this quantity to be as large as possible. And so if this is the margin over here, this is basically equal to this as well, okay? So we can kind of define this as the margin, okay? These two sides are equal. So we can just kind of maximize this quantity over here, 2 over the norm of W, okay? And we want to maximize this, okay? But we can only pick kind of boundary decisions where we're still going to get 100% classification, right? I can't just pick some arbitrary thing and say, you know, like the 2 closest points to this line are like super far away or something. So we want to maximize the margin, which is equal to I should put little arrows over these, which is we wish to maximize the margin, which is equal to that, but the must still achieve 100% separation, okay? Which means for all points, the resulting classification has to be correct, okay? Running out of space here. Okay, and so so there's a little bit of clever math here, and so kind of the constraint should say constraint to make sure all points are classified correctly. Okay, is that the true class is Tn, okay? And we'll say the true class is Tn for point xn, okay? And Tn is gonna either be +1 or -1. And so what we're gonna say is that Tn times W transpose xn plus b has to be greater than or equal to 1, okay? So for xn that are positive, you know, the classifying boundary will classify as positive, and Tn times the classifying decision will be positive, okay? And then for xn that are negative, this decision, the decision boundary, will classify as negative. And, you know, Tn times the decision will be also greater than or equal to 1, okay? So this has to be true. So I guess this must be true for all n. Okay, and so so that's what we've got here. It's and then the book gets all a little bit hand wavy, and I watched a bunch of videos on support vector machines, hoping for a less hand wavy answer. And I don't know, they all just say we're going to put it into a form where we can do quadratic programming, and then that's the answer. And I never learned quadratic programming. I don't know, did you guys learn quadratic programming? Okay, and I haven't found a satisfactory thing other than we can get the answer into some form that uses quadratic programming, and therefore our answers are solved. So we wish to maximize basically 2 over this, okay, which the constant doesn't even matter, okay? Constant 2 doesn't really matter, okay? As far as finding W goes. And so maximizing this basically is equivalent to minimizing W itself, okay? And you can minimize that, and then we'll say subject to okay, so we're going to have this kind of rule, and so anytime you're trying to optimize something, subject to a constraint. Well, you got a few options, but a lot of them will use Lagrange multipliers. Okay, so optimizing with subject to a constraint. And so this will be different for every single kind of point, okay? And basically, if we turn this into kind of a Lagrange thing, we say, you know, well, this has to be Tn times W transpose X n plus B minus 1, okay? This is kind of the zero part, and then you've got some kind of constant, alpha over n, and so we're going to try to optimize basically W transpose W, which is basically this part, minus basically the sum of all of these Lagrange multipliers for all n, okay? We'll say subject to alpha n is greater than or equal to 0 for all n. Okay, and the book goes, the videos all say, like, we can optimize this using quadratic programming. And I find that incredibly unsatisfying, but that's what they say. So, so we can solve. So basically, there's no closed form solution, okay? Okay. But the answer can be found quadratic programming, which I guess. All right, and again, every support vector machine video I found. So there was like one from, I think, Georgia Tech through Udacity. There was like a MIT OpenCourseWare, and I don't know, a bunch of other like short things on YouTube which were of lower quality, but the Georgia Tech one and the MIT ones seem to be the best. They all just said, so we get this into this form, and we can solve it via quadratic programming. Let me just show you what R does. Okay, so, that's that. Okay, you can. I guess I need to update my version of R. There's a package in R called E1071, and it will do all of this with a single line here. Sorry, I had to run all of these previous plots. Okay. And the line's pretty simple. So I just have x2 and x1, and so I say, you know, create SVM where you know, we're predicting y based on x2 and x1 using kind of a linear classifier. And when you create this plot, you get something that looks like this. Let me, okay, and this looks a lot like the one that we kind of drew here. Okay, so this is the same data, just with dots instead of pluses and minuses, and it defines kind of the support vectors or it shows these, and it kind of shows the kind of the classification rule. This was supposed to be a straight line, but just limitations, it's just calculating for all of these points, and it kind of, you get this thing. But okay, so so this is how it could be done in R, and again, if we look at just this, these are really just the 3 points that define the boundary, and so these are known as the support vectors. And the idea is that even if I add additional points or take away some points, you know, I can add more, and it's not going to really change the boundary, okay? As long as I'm not coming any closer, okay? You know, I can add or subtract, you know, I can even like remove this one and it doesn't matter. I can remove this one and it doesn't matter, and I can, you know, remove these, okay? So we can add or remove points other than the support, you know, the support, kind of the support vectors, and the boundary will not change. Okay. So this is kind of our hard margin support vector classifier. Okay. Now we could imagine, if I just go back a few slides. Okay. So before I draw any of these, what if I take this, okay? Okay, and what if I add a point, I don't know, like right here, okay? All right, if I add a point right here, we can still achieve kind of separability, but now, how do I do this? Okay, but now my margin is going to have to be something like this, right? Just with this one point, okay? And so these become my support vectors. Oops. And so, you know, this one point has a lot of influence. Well, I guess technically these three do, but just we used to have like this nice wide margin, and then now we've got this one point. The addition of this point drastically changes the decision boundary. Okay. So, so what we can do is, rather than saying the constraint when we kind of optimize our margin, okay, is we can soften our constraint, okay. So kind of the hard margin constraint was that the true class multiplied by the decision made by the boundary, okay? So again, this is kind of true class label, plus or minus, multiplied by decision made by boundary. We said this always has to be greater than or equal to 1, okay? Now, what we can do is we can create a soft margin, okay? And we're going to say that the true class multiplied by the decision boundary, it can be a little bit less than 1, okay? So I don't know how they draw a xi. How do you draw a lowercase xi, okay? All right, this is lowercase xi. I don't know. I never learned how to. This is how you write xi, right? I don't know. Okay. And it differs, okay, for each one, right? So xi has to be greater than or equal to 0, okay? And so if we have if xi is okay, xi n is between 0 and 1, then the point is between the margins. Just slide everything up a little bit, okay? And then but xi can also be greater than 1, okay? And if xi is greater than 1, then the point is actually on the wrong side of the boundary. Okay? And so, so what we want is we would rather not have xi's that are greater than 1, okay? Because that means our points are on the wrong side of the boundary. So, so what we're going to do is we're going to try to minimize basically the w part plus the sum of the xi's, okay? Ideally, all these xi's are kind of close to 0. But we'll try to minimize basically the sum of both our w's and our xi's, okay? So the soft margin basically says, we'd rather our xi sums n be quite small, okay? 0 is ideal, but we can allow xi to n even be greater than 1 and misclassify a point. And misclassify a point if it means kind of better other properties, right? So, so we minimize basically W transpose W plus some constant times the sum of all the xi's. Okay, subject to basically the x's have to be greater than 0, and the classification of each point has to be greater than, whatever we've defined, okay, for all n. So if I kind of bring this thing back, so this is what we've got now. So now we've added this, and basically the C is a kind of some kind of parameter to define like which of these priorities are more important. Is it more important to minimize the sum of the x's, or is it more important to minimize this? Okay, so this is a kind of a weighting factor. So kind of like when we did regularization, is it more important to minimize the complexity or more important to minimize the sum of squares? It's kind of like that. Now we have kind of two competing priorities, one being minimizing this, which is going to maximize the margin, but also maybe we'll allow some things to be misclassified, okay? To decide which objective is more important. Okay, so just to kind of go back, if this is what we have and I don't remember exactly where I drew that dot, but it was somewhere. Oh, we're gonna run out of time, I know. Okay, so I drew it like right there. Okay, so I think. So I put some kind of like a blue dot right here, right? This was our new point. What we can do is we can still draw the margin kind of like this, right? And this will okay, this is supposed to be, so we're still kind of maximizing the W here, okay, or maximize the margin. But this one is misclassified, which means basically the xi on this thing is greater than 1. Okay, so it's on the wrong side of the margin. So its xi is wrong, but maybe this is an acceptable trade-off here. Okay, all right. We'll end here. We'll see you guys on Wednesday for the midterm, and then we'll continue on Friday.